So, everyone full of food, good. So you can listen to QuantumPower Workshop. That is almost held almost at the end of the project QuantumPower that started in 2019. And yeah, this project is aimed at tying together Josephson devices and measurement of power and to automatize everything as possible. So the first will talk Bernard, that will tell you something about the project itself. Then there will be talk by Ricardo about our hardware, and in the end I will talk to you and I will tell you something about the measurements results, and I will show you real measurements in life. Yeah, it's yeah. Okay, sorry.
Yes, hello. I'm going to talk a little about the QuantumPower and give a short introduction about it. So basically what it is, it's an open source quantum traceable AC power standard, and has been the result from this project. There? Yeah. In short, this project has been the culmination of quite a few different projects that has happened in Euromet over the years. So it has involved Josephson voltage standards, different tools for analyzing and sampling of techniques of voltage, and of course some things about transducers as well. Basically, what we are trying to do in this project is to tie power sampling techniques much closer to like a quantum-based SI system, where we are sampling electrical power and then having it directly calibrated versus a programmable Josephson voltage standard. So here you can see the full system. Basically, we are trying to take in some old existing components. That is basically the programmable Josephson voltage standards, or PJVS, and ADC sampling equipment, namely the 3458 and 5922. And also some older software, the TVM, quantum voltage toolbox, algorithms, and then including some new components, namely software control, multiplexer, data processing, and direct calibration of the ADCs. So here you see the main new hardware from this project. That is a multiplexer, much developed from INTI, and has also been made by quite a few of the European institutes. Basically what it does is that it takes in voltage, current, and a quantum accurate programmable voltage standard, Josephson 1. And then you have 3 digitizers as an output from this multiplexer, where you switch between voltage, current, and PJVS to have a real-time calibration of the digitizers. So basically it's photovoltaic relays that switch between these channels, and we do direct sampling in this project because that was what was easiest to implement successfully by the institutes. So one of the points is to make all of this open source and try to build the capability of all of these institutes and other institutes afterwards to make use of these techniques. Further, the multiplexer assembly and testing. We so far we know about 6 separate multiplexers that have been constructed and tested to be quite good. And we have low on-state resistance, which means low errors in amplitude and phase compared to what we're actually measuring. The goal was for this multiplexer to be within 2 microvolts per volt, and we are already well inside it, as I understand. And of course, what we hope for as an output is that even more institutes start to use this open source design for this multiplexer and test it. And it's relatively easy to implement. Maybe you can have a summer student build it, for instance. Then one output is the upgrade of the TWM software. One of the upgrades is that now we also have a software for the multiplexer that is directly implemented into the TWM software. But you can also use the multiplexer outside, and you don't necessarily have to use a multiplexer either in the TWM. But you have the option of using it, not using it, using the multiplexer outside, whatever you choose. Or a totally different multiplexer if you so choose to do that. But also, you can, of course, use the multiplexer without the Josephson standards. But anyway, that is our intention, to use it with Josephson. So, the control software of the multiplexer. Here you see different sequences of different voltage inputs for the digitizer. And here under you see the transition between a sine wave that is taken in to be sampled, and then the transition to a programmable Josephson voltage standard where we have a sine wave approximated, or a stepwise approximated sine wave. Let's see. And this software, it can directly access the TWM software, and you can choose different kind of triggering, internal, external, programmable based ones. And yeah, you can even use it to choose any kind of switching sequence that you want. You don't have to use this exact switching between current, voltage, and PJVS inputs, but that is our intention to switch between them. So you're kind of free to use it outside of these specific applications that we have in this project. Then what you can do with the sorting sampling data is that you can select how many points you are going to sample from the, say, for instance, the input signal that you want to measure, how many points on each of these stepwise plateaus that you want to measure, and how many points in the transition between steps and different sequences that you want to like skip, because you get, as I showed in one of the previous figures, you get some, what should I say, not so good data in between. So you basically want to measure the good data. And here you see some of the sampler calibration. We get a linear fit for the sampler based on input from the PJVS. And here you see various errors that you get from the linear fit. So what you can see is it's within 1 to the minus fifth. Further, here is some of the actual measurements that we have done. That is a comparison between our system, the QuantumPower system, and the AC quantum voltmeter from Supracon. What Supracon has done is that they have a differential method. So they have a different method than the one that we are using. And the object that we are measuring on here, they are the same. It's the Fluke 5720. So, well, the AC quantum voltmeter does have smaller errors, but what they need is a lot more time to measure compared to the QuantumPower system. So they need hours, whereas we need like 20, 30 minutes. And the test signal is 0.8 volt RMS at 60 hertz. So the future from this is that we have an open source collaboration. We have made an open circuit design, open source design of the quantum power measurements and results and software, and all of those details, they are available on GitHub and on the YouTube. The design is modular, like I explained. You can choose to have some of the components, you can choose to not have some of them. And yeah, you can implement it to varying degrees in different laboratories. And yeah, you can adapt it to new ADCs and PJPS systems and measure power, phasor, AC, current, tying it to the SI. Currently, there are still no CMCs for AC Josephson, but this can serve as a validation in comparisons and make things available. And then we have suggested a follow-up project, the quantum sampling. Yeah, and that will be discussed later. Any questions?
Maybe we can keep questions after all the three presentations, because everything will get more discussed in detail.
Okay.
So now we can continue with Ricardo's talk about the multiplexer itself.
Okay, yeah. Hello, everybody. I'm really happy to be here. And before I start, I would like to thank all the people who helped me to be here. So I will start talking about the multiplexer design for this quantum project, QuantumPower project. So the outline of the talk is we start with the design specification, how we select the solid state relay, the connection diagram, some schematics, some description of the multiplexer, the slave boards, the controller, the enclosure and the cabinet, to speak about the firmware and the software you can use to control the multiplexer. Some measurements we did at INTI for characterization. Some measurement scenarios you can choose, and at the end, another application of this multiplexer, just not only for power measurements. The multiplexer was the tags of the working package 1. These are the partners of the working package 1. We did all together. We decide and what to do and how to do. And mainly the design and decision was made by INTI. So as Bernard said, it's an open hardware, so you can find all the instructions and to build your own multiplexer on the GitHub. So the specification to build the multiplexers are here. The uncertainty contributions should be less than 0.1 ppm at line frequency. The bounce-free operation. Reversible operation, this means that you can use I will tell you later, but the slave board, just 2 input, 1 output, or 1 input, 2 outputs. So you can reverse the input or the output as you want. We use communication with the PC by the USB connection. For connecting the voltage and current and the Josephson, we use BNC connectors. The maximum input voltage you can apply is 10 volt. Besides, the relays support more, but this was the start specification. The input frequency you can apply is 1 kilohertz, and we included an external trigger just to switch between the inputs and output synchronous with the sampling system and the generators. So first, the design consideration we take into account is what kind of switches or relays to use, CMOS or photovoltaic. We have to take into account the on resistance because it's, you add in the signal path a switch. This switch has a certain amount of resistance. So this resistance is in series because can cause an error in the amplitude you measure. Also the off isolation, when you switch off the switch, there also comes some errors. So some leakage you could have in your measurement system. The speed, so the turn on and turn off time, the crosstalk between channels, because you want to, the main idea is to measure power, so the phase shift should be lower as possible. And how should be the PCB? See, the PCB is 2 layers, 4 layers. So this was the first considerations we used to select all the components of the multiplex. The design concept is to have a master unit or control unit. This is in charge to make the communication with the PC and store the sequence in memory you want to use to switch with the different channels. And to have some slave unit where are some control logic and the relays. So the solid state relays on this board. You could have many, not so many, I will tell you later, the amount of slave units per control unit. So in one multiplexer, you could have 1 control unit and a number of slave units. So the selection of the relays. So we have considered 2 types, the CMOS and the photovoltaics. Which one? Well, we'll see. The This is a table comparing both of them. The CMOS relays are easy to use. Also the photovoltaics. The series resistance in case of the CMOS is medium value and the photovoltaic is low value. The CMOS are more high speed, so the switching time is lower than in photovoltaic case, but in case of the photovoltaic, you can reduce this time using a special RC network on the activation LED or LLD. The power consumption is low for the CMOS path and medium power for the photovoltaic, but what is important, the photovoltaic are isolated by itself. So it's a phototransistor and an emitter, a light emitter, but LED. In the case of CMOS, it's difficult to isolate because you need to power. So you have to isolate two powers. Some specifications of both families. So here is the on resistance. You see the CMOS has 1 ohm typically, and the photovoltaic is length 0.1, 0.2 ohms in series. The control current here is too much because you have to, is higher than in the CMOS case, because you have to feed current to a LED diode, so you need current. But we decide to use the photovoltaic relay. In case in comparison, the on resistance, because it's one of the considerations, one of the most important, because this has a serial resistance on the path, on the signal path. We can see that the photovoltaic serial resistance depends only on temperature. But in the CMOS case, depends on temperature, also on the voltage you apply to the switch. So the supplier specify on the data sheet the flatness of its on resistance, but this could cause a trouble when we are using in high precision measurement. This was another reason to choose the photovoltaic relays. The connection diagrams we can use to use 3 signals: current, voltage, and PCBAs, and 1 digitizer. This also is a part of the consideration on the design. Or you can use 2 digitizers just to feed current in one digitizer, voltage in another digitizer, but the PCBA is to calibrate them to each one. Also, you can use, it's possible to use in the differential sampling. This is connected as a differential voltmeter, the PCBAs together with the digitizer. So you select current or voltage. The schematics is, first we design a 2-to-1 slave board, so it means two inputs, 1 output, or the other way around, 1 input, 2 output. To increase the isolation of the multiplexer, we use a T scheme, and you can see the T here in vertical. So the signal is coming from the input, in this case, through the output. And then when this channel is closed, and when the channel is open, this relay is closed, but these two are open, making a T scheme connection. So this increases the off isolation. We can see And also here you can see the RC network here to increase, to reduce the turn on and the turn on time. So when you send the signal, okay, close this relay, this RC network decrease the turn on time. What's important to note here is this point. I will go later on, but this should be connected to the measuring ground circuit. It's an external ground connection to the multiplexer, and it's mandatory for the T scheme. So if you not connect this ground, the T scheme doesn't work. So this is a more scheme of the T. So when the signal part is open, this point is connected to ground, and when the signal part is closed, so it means S1 and S2 is closed, S3 is open. Also, we add a GAR connection. It's possible to add a potential, external potential to the multiplexer. We will see later how is this GAR is going on the signal path. This is independent of if you want to close one channel or another, you can close at the beginning of your measurement or just to leave open. This is a three-dimensional picture or graph from the software I used to do the PC board. So because it's open hardware, we use open software. This was made by KaiKai. So you see here the relays and the external connections and the logical control. And it was a Euro size car, so you can put in any cabinet with these dimensions, which is normalized. This is the bottom side, and here one layer is for the high potential, and the bottom layer is for the low potential, and also for the GAR relays. So the front view of the slave board and the side view, how it looks like, on how it should look like when you build the multiplexer. Here is a photo of one of the board. This is the bottom, the top layer is the path for the high potential, and the bottom layer is for the low potential, and you see here two ground planes. So this is two-layer board. This is the ground plane for the digital control signals, and here at the edge of the PC board is the ground for the measurement circuit. So you can see the isolation here. Yeah. So it's isolated, it's completely isolated from the digital part. Well, the bottom layer is equal to the top layer, but is used for the low potential path of the signal. It's a photo on the enclosure, on the cabinet, just in vertical position, with some cables to the master board to control and to close and open all the relays. This is the GAR part. As you see, I mentioned before, we have the GAR part just close to the line of the signal path. You can connect an external potential to this point, or to this point, and you can select which one to use. I think it's clear also on this picture, the signal path for the low potential and for the high potential will keep as close as possible and with the same length, because we have to preserve the phase between both channels, or not to introduce a lot of phase error when you want to measure. And then come to build a 4-to-1 slave. This is not reversible system. So you have 4 inputs and 1 output. It's just only to put 2 boards, 2-to-1, one opposite to the other. You see here is one of the slave, the other one of the slave, and here in the center part are the connections and the relays. This has the double side of the other one, but also fit in narrow car cabinet. And the center connector is the output, and these are the 4 input. And here you have the digital control signal to close and open the relays. One idea from Bruno from INRIM is to use 2 of these 2-to-1 slate to build 1-to-4. He made this connection, the center connector was soldered together, and he added a board in between, just a solid metal board to isolate both of the slave board. Or you can use, instead of soldering the center connector, just to use SMI connector and a T, as you can see on these three-dimensional pictures. The controller, now we shift to the controller board. We use, for simplicity and because it's open hardware and open software, an Arduino. It's based on an Arduino Mega. We use a special design which is smaller than the original Arduino. So using this, we can connect 6 slave boards 2-to-1 or 3 slave boards 4-to-1. So it's up to 12 channels. You have 12 channels in one multiplexer. So then we design the controller board. The controller boards, you can plug the microcontroller here in the center. Then you have connectors to the different slave board. You see 6 connectors here, and also connectors for the display on the front-end panel, and the push button also in the front panel, and the trigger-in signal. So here is an isolator, so the trigger signal is also isolator for the power supply of the digital part of the multiplexer. And here at the other edge is the power supply. This is a photo of the PC board. It's also 2 layers and also Eurocard size. This is a draw of the push button board. You have 4 push buttons, 1 to reset, 1 is to change the condition of the channel. You can close and open channel by channel. Another is to clear, and then another one is to stop the sequence. The display. So when you power on the system, the display informs you how many slave boards are connected here says that we have a slave board number 1 and a slave board number 2, and it's an internal clock and it's in local operation. The master board and the front panel board on the on the cabinet. The picture of this. The enclosure, we use an euro car size, so we need an euro car enclosure to have at least 6. We can use 6 slave board, 2 to 1, and 1 master board. So I need at least 7 slots to put all the boards of the multiplexer. And here is the push button operation. Local remote, enable channel means to close the channel, reset the multiplexer. This is a software reset, just to put the multiplexer in power on state, but this reset doesn't erase the memory of the controller board, but you have here the microcontroller reset, and this reset everything. So if you have programmed a sequence to run, you have to reprogram again. This is information how to wire the board to the front panel connectors and how to connect the ground to the measurement system ground. The diagram of one of the disposal of the front panel. So this information is also the heat up, and also you can see it later on the lab. And this is the display and the push button and the USB communication to the PC and the external trigger signal and the ground of the multiplexer. And this is the guard connection. And the other one is the BNC connectors to the different signals to the multiplexer. And in the center are the output. It's a picture of one of our multiplexer we built at Tinti with 2 slave boards. And this is the multiplexer that Bruno had built at INRIM. You see here the 6 multiplexer slave board and how it was connected on the display, the push buttons. There's a photograph of the enclosure with the 2 slave board and the master board. The firmware. So now we implement a certain commands on the multiplexer to open and close the channels, to reset and to load a sequence so you can let the multiplexer running for a long time until you stop it. The most important is you can set the trigger polarity, and the trigger should be internal or external. Trigger polarity positive or negative. You can program a timer, an internal timer. And this is in sense when you are using internal trigger. And then common commands you have on certain instruments. And then enable on and off to close and open one of the relays. And you can ask to the multiplexer the state of this channel. And here you have how to add the sequence. The sequence is in automatic mode to close and open the channels. We will see later. And also we implement a status byte, so you can ask to the multiplexer if some error happened. You can ask the multiplexer which was the error. It's a power on state. When you power on, you have this all channels are open, all GAR are open, local operation, trigger internal, 1 second internal timer, and only one sequence in memory. You can use for the push button on the front panel, switch from channel 1, channel 2, channel 3, and then back to channel 1. And this is one of the main part of the firmware. You can store in memory a sequence. The sequence are organized in a certain matrix. The columns say the slave of the channel you want to close, and the column is, the row is the state. It's closed and open, and you have to specify the time, the time in trigger pulses that the multiplexer stay on this sequence. And then when external trigger comes, they move to another state of this matrix sequence. Here is more, maybe it's more clear. You wait for the multiplexer to arm. This is the condition, and you have the command to start the multiplexing. The multiplexer is wait for external trigger, and when the external trigger is there, go to the sequence number 1. You receive the stop command, go to a needle state. If not, wait for another trigger. When the triggers come and the number of triggers you program have passed, they move to the sequence number 2, and this is running all the time until the multiplexer receives the stop command. So to arm the multiplexer is mandatory. You have at least one sequence in memory. This is done in its flow chart. Then to disarm the multiplexer, you have to send a stop command and the clear command. And this is the sequence, the default sequence, which are in power on state. You push the button on the front panel, switch channel 1, then you push again, switch to channel 2, and then push again, switch to channel 3, and then back again to channel 1. The standalone software, this was made by Martin. So you have the control in a standalone application of the multiplexer. You can program to close and open the channel on this window, to get the state or the status of all channels. One channel is closed, for instance, and you press this button and one of these get green, just indicating that this channel is closed. And here is the important part when you can program the sequence. As I said before, it's like a matrix. In the column, you have the channels, slave 1, channel 1, slave 1, channel 2, slave 2 is channel 1 or channel 3, channel 4, and so on. And on the row, you program the states. So this, when it's green, it means it's closed. And here is the number of periods and the number of triggers which this channel remains closed. So in this example, 10 trigger signals. Then this sequence can be stored in a file, and you can load with the software, and then you can upload to the multiplexer, or you can download from the multiplexer. Also is another standalone software was made, it's a console software made in Python, and to load the sequence in the multiplexer was done in LabVIEW. Well, we did a few characterization, but most of the characterization of the multiplexer was done for another partner of the project. In RIM have characterized the error in voltage. GBA have characterized the phase error, SEM also characterizes phase error and amplitude error. We measure the on resistance at different temperature. We put the multiplexer in a chamber, we change the temperature, and we measure the series resistance. And you can see this division is 2 milliohms. And if we sum up one of these, the variation of the on resistance was, I would say, 15 microohms in 3 hours of measurements. Also, we measure, this was done by Marcos, my colleague Marcos. Also, we measure the off isolation and the crosstalk between channels using an oscilloscope, a lock-in, and a spectrum analyzer. And we can see that at 1 kilohertz input signal frequency, the crosstalk is below 100 dB. And also the off isolation at 1 kilohertz signal is below 100 dB. The turn on and turn off time, the turn on time was measured to be 450 microseconds. The turn off time was measured to be 800 microseconds. If you compare with the data sheet, it's much lower. This is due to the RC network we add to the multiplexer, to the relay path to activate them. And different measurement scenarios you can use this multiplexer is when you have 1 PGA, 1 dBm, and you want to sample two signals, so voltage, current, and the Josephson. You have to connect, in case you have only 2 slave board, 2 to 1, you have to connect the inner connection to the dBm. And the sequence you have is channel voltage, current, and Josephson. This is one possibility. This is an example. Here you have Josephson, could be voltage, current, and then the other signal. In case you have 2 dBms, you need more slave board. You need 3 slave board. So 1 dBm is connected this way to measure voltage. The other dBm is to measure current. And then you have to connect the dBm to measure the Josephson signal. And this one could be one of the sequence to measure. In case you have 3 dBms, 4 slave board, in this case, you need 4 slave board. You measure voltage, current, and the Josephson. This one could be one of the scheme. Another scheme is with 5 slave board, also 3 dBms, 1 PGBs. This one scheme could be this one. And in the case you have a 4-to-1 slave board, it's more simple because now you don't need to connect externally to a slave board. So just you connect the dBm in the center of the front panel, and you have voltage, current, and Josephson signal at the output. And if you have 2 dBms, now you need to add an external connection for voltage and for current, and you need 3 slave board. So 1 PGF and 3 dBms. You want to measure 3-phase system with 3 dBms. And just to be an end, I want to show you some other applications. I asked a colleague of mine to use this multiplexer to measure capacitors. So he measured 100 picofarad, 1000 picofarad with the Allen-Harley bridge passing through the multiplexer and with direct connection, and he made a deviation of both measurements. And we can see that fit on the uncertainty of the bridge. He also measured 10 picofarad, but with 10 picofarad, it fails. So the deviation was outside the uncertainty of the bridge. So if you want to build your multiplexer, you can use, for instance, for measure capacitance or impedance. So that's all for me. Thank you.
And now I will talk about some results we made with the system. Pardon. Nope. So now you have got some idea how this system works. I will try not to repeat what was already said, but I will show you how it can improve, be useful for you, maybe not all of you, but some of you. So just to be sure that you know what this project was about. It was about automatization, to make everything just push a single button and the system will measure your power source as precisely as possible. Because there was some previous project, TracePQM, that produced a method and software with sampling software and algorithms to calculate the power. We thought that we can use the software and use Josephson to calibrate the digitizers and to simplify the measurements and everything. Because yes, all of you know how to calibrate the digitizer to, I don't know, ppm level or better, but how long does it take you to do it? You have to spend some time before the measurements, after the measurements to check it. And this system is about that all the digitizer calibration is made automatically using the Josephson. And of course, you can decrease the uncertainty because you are calibrating just before the actual measurement or after, and it's done automatically and so on. For example, our CMI uncertainties for power measurements, the contributions are 1/3 is of the shunt, 1/3 is of the voltage divider, and 1/3 is of the digitizers. Using this system, we automatize the calibration of the digitizers and almost essentially remove the uncertainty of the digitizers because they are calibrated by the Josephson. So we can decrease our uncertainties for the power measurements and simplify it. Up to it, there is such a possibility that the Josephson, at least my Josephson, got its such a problem that I cannot measure any frequency I want. Because if I use differential measurement, then the Josephson must be coherent to the source or to the measured signal. And thus I cannot make a coherence for any frequency, just only some set of frequencies. But using this system, we can rely on the digitizer if the gain of the digitizer is not changing much with frequency, or at least in some small range. We can measure any source of any frequency using the Josephson. For example, if we got a source of 53 Hertz, and I can generate on the Josephson only 60 Hertz, I can say, for example, that this digitizer is quite good and the gain doesn't change much with frequency. So I calibrate the digitizer on the frequency of 60 Hertz and use it to measure the source of 53 Hertz. So all the idea is in effect based on the old measurement by Louis and Ralph and others, I believe. It's a paper from 2009. They used a multiplexer to measure the power, but this work was not, I don't know, developed more. So in effect, it's a quite old idea. Yeah, colleagues said it already that when we got a multiplexer that is synchronous, we can make multiple setups or multiplexing schemes that can be useful for different scenarios. And for the power, there are two very important things. For example, we can measure power in this system. First, we will use one digitizer to measure a voltage. Then we will switch the multiplexer and use the digitizer to measure the current. And then we can switch the multiplexer and we will measure the Josephson, and this Josephson will be used to calibrate the digitizer itself. And from the voltage and current and amplitudes and phases, we can calculate the power. But this this setup needs synchronous, everything should be coherent because we are multiplexing in time. So if everything is coherent, we can use, for example, FFT to calculate the results, and we should get power. But we do not always have a coherent source, as I said. So, for example, we can use this measurement setup. First, we send Josephson to second digitizer. Then we sent Josephson to first digitizer. We used this data to calibrate both digitizers. And then we measured the current and voltage at once. And in this setup, we can use a different algorithm, time domain integration, that is not so demanding on the coherency. And again, we can measure the power, but in other case. And so on, we can think about other scenarios. Others already talked about it. So, how does it work in a real life? First we run measurements with the multiplexer setup. Yeah, we connect the Josephson, the power source, chance dividers, everything together. Control computer. When we run it according to one of the selected scenarios, and everything is sampled at once as a continuous samples of the digitizer. Next, there is data processing. That is the one of the most important parts. And the script will calculate the gain of the digitizer using the sections where the Josephson was sampled by the digitizer. Then this calculated gain is corrected in, this gain is used to correct the sections where the power source was measured. And then we use some selected algorithm, for example, FFT or time domain integration to calculate the actual power or amplitude or what we need. So the first question is, what is the error caused by the multiplexer? How does it affect our measurements? For this, I have I have taken a calibrator Fluke 5720, everyone knows it. And I have measured it alternately by classic differential method, PGVS differential method at 60 Hertz. And then I have used this, I call it QuantumPower or multiplexing method. For this, I have used, I do not have it here later. I have just, in the multiplexing method, I have just switched between the voltage of the calibrator and the Josephson, and voltage of the calibrator and Josephson repeated many times. For the actual Josephson part, I have sampled 12 periods of the Josephson. In effect, I have used only 10, and the first and last period of the Josephson was thrown out because the multiplexer settles down. So I have cut out this data. And for the calibrator, I have sampled 100 periods, and again, one before and one after was thrown out. And the measurement was almost coherent. The calibrator can be phase locked to the system, but the coherency is not perfect. So I have selected 100 periods just to be sure that there are no windowing error of the FFT or some other algorithm. In the end, I have used PSFE algorithm, but the FFT got very similar results. The connection setup was quite complex. Here we got the multiplexer, here is the calibrator, Josephson, digitizer, control computers, and everything triggered to generate triggers for the multiplexer. But the most important thing is to ground everything to Josephson. Otherwise, I couldn't get proper values. As a trigger, I used HP33120A. It's an arbitrary waveform generator. They just generate pulses to the multiplexer and to the digitizer. So this is how the sample data looks. It's just the beginning. First, here we have a section of the sample Josephson waveform of 60 Hertz staircase waveform. And here is the calibrator itself. It's offsetted in the voltage because it's easier to, when there are more signals, it's easier to look at it. And you can see at the beginning, there is the error when the multiplexer switch and settles down. So usually I take samples approximately about 1 period and cut them out at the beginning and also at the end, but maybe it's not so, it's not needed, but just to be sure. And when all the processing runs, I get a lot of useful information. For example, here you can see the development of the gain of the digitizer as was calibrated by the Josephson in time. This is about 1 minute measurement. And you see this 5922 digitizer is changing the gain quite a lot during the 1 minute. The standard deviation of this data is about 2 microvolts. But always there is a section of Josephson when the gain is calculated, then there is after multiplexer switch section of the calibrator. So we use this gain calibration to the next section. Then again, we measure Josephson, calculate a new gain, apply it to the next section when the calibrator was measured, and so on and so on. This is the gain. Here is offset. It was about -22 microvolt. But the most interesting is that the gain error of the digitizer was 90 microvolts per volt. It was not calibrated for a very long time. It was just not needed. It was usually used as a transfer standard or something like that. So I was quite happy that there is such a big error, so I can see that the system works. And for example, during the data processing, I can also see the nonlinearity of the digitizer. And you see that the digitizer got some few microvolts nonlinearity. Maybe in next versions of the algorithm, I will try to do something with this nonlinearity, but it's some future work. So, and this is the result what I got. The red, the blue rectangles is the measurement using differential method. So classical Josephson differential method measurement is the amplitude of the calibrator, and on the y-axis, you can see difference from nominal value, which was at 0.8 volt RMS at 60 Hertz. And this orange points is the measurement using the multiplexer setup. And the error between these two methods was 0.3 microvolts. It's or microvolt per volt, 0.33. So from this, we can see that the multiplexer doesn't add much error to the measurement of the voltage. I was quite happy that I got this result, so I could continue with the actual power measurements. One important thing, why do you see such a big spread in the multiplexer measurements against this smaller spread of differential method measurements? This is because these multiplexer measurements are much faster. This point of differential measurement is about 100 seconds, but this orange point is about 2 seconds. So if we will take a look at the length deviation, the red one is the multiplexer measurements, and the blue one is the differential method measurements. We can see that the spread of the results is even smaller with the multiplexer measurements. But I have to make more proper measurements for longer time to see how the length deviation shows up in longer times. So I have found that the amplitude error caused by the multiplexer is sufficiently small for power measurements. Our goal was to get below 1 ppm. I got 0.3 ppm. The most important was the grounding setup. I have spent a few weeks to get everything working. And you see the method is quite fast. I can see what happens with the calibrator in shorter time than with the differential measurement. But I have to say this is a differential method as implemented by Supracon. If you make it yourself, you can get also these slower, faster data probably. But I wasn't going to develop a whole new software for differential method. So power measurement, now I knew that the voltage measurement was correct, so I could start power measurements. For this, we got power meter Radian 22, which was used as a reference. That was delivered by PTB. Thank you for this. And this reference was used in Euramet comparison, so we knew that its errors, and it is a very good device for measurement of power. As a power source, I have used Flux 6100A. And I have measured this power source alternately by this Radian, our reference, and by our setup. The power was set at 240 volts, 5 amperes at 53 hertz for several power factors, 0, 0.51. The transducers, shunt, and divider were delivered by Bruno from INRIM. The idea of this project is to automatize and simplify digitizer calibration, not to make a new power measurement comparison or anything. So these transducers and this Radian power sources, power meter is traveling between my institute and Norway Institute, and then it will go to INRIM again. And we will just do comparison with the same transducers to be sure that our errors are not caused by the transducers, but only by the method. So we will all be measuring with the same transducers. Again, I was trying to develop a proper connection setup. It's again quite a mess. The grounding was issued, the oscilloscope was causing errors, but I have maintained to get everything working. I had to remove the HP trigger source and replace it by a National Instruments device, because the HP trigger source was causing 20 ppm errors when I was measuring power. I have no idea why. But in the end, I was quite happy with the setup. Because at CMI, we have two power sources, Flux 6100, that is quite hard to synchronize, and Flux 6105. That is easy to synchronize, but is used most of the time for customer calibrations because it was a very hard time 2 months ago, and every customer wanted to do calibrations at once. And so I was limited. I had to use this 6100. And I said to myself, okay, if I cannot make a proper synchronization, a really perfect coherent measurement, let's try to make a worst case setup and let's make a non-coherent measurement, because it was also one of the goals of the project. So I have made the setup in such a way that everything was non-coherent. The power source signal was 53 Hertz. The digitizer was not synchronized to the power source and was sampling at 50 kilosamples per second, but different time base. And the PJVS was, my PJVS is not able to generate 53 Hertz signal, so I have used 60 Hertz signal. And again, the time bases were not tied together. So it was a system with 3 independent clock, and it was really the worst case setup to know what I can achieve. As I said, with the multiplexer, we have different possibilities. We can use time multiplexing, use one digitizer, and this digitizer will measure first the Josephson to get its calibration, then voltage, then current. But this is useful only for coherent setups. Yeah, otherwise you get big errors. So I have used 2 digitizers, and I was simultaneously measuring voltage and current, and I have used power time domain integration algorithm to calculate the actual power. And the timing was such that first I have used 10 periods to calibrate the first digitizer. So I have used multiplexer to connect Josephson to the first digitizer. Then I have connected Josephson to the second digitizer. And then I have connected voltage to first digitizer and current to the second simultaneously. How does it look? Yeah, this is general overview. These are the actual measured data after data processing. So, of course, these voltages are offsetted, so it's easy to see the signals. First, the Josephson is connected to the second digitizer, is this part, then it's connected to the first digitizer, this part, and then first and second digitizers are measuring voltage and current simultaneously. Again, the sampling card got quite a big errors. The first channel got about 100 microvolts per volt gain error. The second was 70 microvolts per volt error. So it's an error much bigger than our final errors. So we know the system works. And these are the results. So again, this is non-coherent measurement. And we got about 16 or 25, 24 ppm is the worst case error. Yeah, it is not the best, but still we have to think about that this is not a non-coherent measurement, and I have spent 0 time calibrating the digitizer itself. Everything was automatic. When the radiant device and the transducers will come back from the Norway, I will finish the measurements for the coherent setup, and I expect much smaller uncertainties. So, as colleagues said, we have developed some software. It's quite a complex thing, but there are 2 important things. The QPS control is used to just start everything, to start the trigger, start the Josephson, start the sampling software, and so on. Then we got a sampling software that controls the multiplexer and the digitizers and starts the data processing. It's done using the QWave toolbox. This QWave toolbox was developed in a QWave project. And it's just a set of many useful algorithms. And this QWave toolbox applies newly developed algorithm to process these measurements. And this algorithm reorders everything and finds out what part belongs where after the multiplexer switches and calls power our algorithm to the useful data. So in effect, what has the new algorithm to do is that, for example, if we got 3 digitizers measuring Josephson or current or voltage, and the multiplexer is switching the signals between the digitizers, the new algorithm have to order all the signals into the proper parts, and so we know what is what and to use the data. Yeah, as I said, the algorithm can do this, that when the digitizer measures the Josephson signal, we use this Josephson signal to calibrate the digitizer, and then this calibration we use for the signal that was measured by the same digitizer later. So the algorithm to process the data have to demultiplex, have to split the measured signal into several sections in between multiplexer switches. It have to find out in the Josephson signal what are the steps of the Josephson, and to using these steps to calibrate the digitizer, to calibrate the gain of the digitizer, then to apply this calculated gain to the other sections with the signal we are measuring, and then calculate amplitude or power from the actual signal. The algorithm can also plot many features to show you if everything is working correctly and so on. For example, it can show you the beginning of the waveform, so you can see that the multiplexer settles quickly enough before you start taking the data after the black line. So you know that, that you cut out the beginning of the data correctly. You can also see that the algorithm properly identifies Josephson steps. All these yellow circles denotes the beginning of the Josephson step or change of the step from one quantum number to another. Here you can see also if all the ringings in the Josephson steps were removed properly. So you do not see any disturbances on the beginning of the Josephson step or at the end. It can also plot you nonlinearity of the digitizers, so you can check if there is some big issue or not. In the case here was some error because 50 microvolt is too much. You can also see the spectrum to see if your measurement is really coherent or not. In this case, you can see non-coherent measurement. So you know that you cannot use simple FFT, you need at least windowed FFT or time domain integration or some better other things. Yeah, so this is data processing, and this is how the control software looks. It's very simple LabVIEW software, not something special. It just allows you to set up Josephson, TWM, the sampling software TWM, trigger, and the actual measurement. And here you can select this multiplexer switching scenario and the timing and so on to run the system according to your needs. But the software can show you how to connect everything. So it's mainly for me, so I do not have to remember what were the connections and how the waveform will be looking like according to the scenario you select. As was said, everything is open source. The control software, the sampling software, TWM developed in previous projects, in the toolbox developed in previous project, the multiplexer schematics are also open source. So this is some, how does it look and how does it work? So next, I can show you live how the system works using the remote control of computer in my laboratory. So people online can see also something. And after that, we can go to the laboratory to look at the real hardware. But maybe if you have some questions, ask them now. It's the best time, maybe.
So this system is mainly intended for power frequencies, but how high in frequency can you actually measure reliably with this?
I haven't made any measurements to check it for higher frequencies because it's not part of the project. I have to do it, but haven't done yet. Yeah. After the end of the project, I can play with this thing.
Okay, thank you.
I think the specification of the superconductor system is 2 kilohertz. They specify everything up to 2 kilohertz. I don't know if it's possible to go even higher. I don't know.
Yeah, of course, it depends on the Josephson, because what does this software do is just switch the signals. And then from the Josephson data, it calculates something and applies somewhere else. So if you got fast Josephson, you can go to higher frequencies, but it doesn't implement any special subsampling as Ralph was doing. No, at least not yet. Yeah. So it's just a typical programmable Josephson range of frequencies.
Multiplexer bandwidth?
Ricardo, do you know bandwidth of the multiplexer? But it's limited by the by the switching, yeah, of course. But the signal itself, how fast it can go through, Ricardo knows.
You can use to 10 kilohertz signal, yeah, or even more. Yeah.
Maybe some questions online.
Yes, hi. You showed some results from the power calibration. What is the phase accuracy that you aim at?
Phase accuracy. Ricardo, I believe you had some slide with phase accuracy.
No. The phase error in time was about few nanoseconds, but I don't remember because it was done with, I think, with SIM or VTT. I don't remember who made the phase error.
Yeah, in few nanoseconds.
Okay. And another question, well, you use these photovoltaic relays, and why didn't you use standard relays? Why did you go for the solid state relays?
You mean the mechanical relays?
Yeah.
Because this system you can make running all the time. Mechanical relay has a lifetime life even lower. So, and the time you need to close and open are much higher.
Okay.
The system runs automatically a long time.
Okay.
Yeah, because even, for example, for this measurement, you can see many points, and for every point, the multiplexer was switched several times already. So it's maybe thousands of switches already in few minutes.
Okay. And another point, you mentioned that there is some self-heating of this photovoltaic switches. Does this has any influence due to thermoelectric voltages if you use it in the sampling mode, where you measure some differential voltages?
No, we haven't seen any effect of the self-heating because we use in the lab. So the temperature in the lab is quite constant, and you apply using a high impedance digitizer. The current through the contacts is quite low. So there is not self-heating, or we didn't see any effect.
Okay, thank you.
I knew that someone will ask. In this gap, I was trying to measure with batteries, to do the same measurement with batteries powering the digitizer, but there was no real difference. But I saw that I couldn't implement it because it was different setup. Yeah, and other testing and some playing with the grounds. Yeah, I believe there is no other question. Some question? Yeah.
One of the two thoughts concerning the mechanical relays, two further thoughts. The contacts bounce, and in the beginning there was the demand that the contacts should not bounce. And secondly, it is quite expensive. It's possible, but it's quite expensive to obtain a high channel isolation, because you need coaxial relays then, and they are not cheap at all.
Yeah, they are very expensive.
Yeah, right. Okay, thank you.
So maybe I will show you, I will connect to other computer and I will show you how this works. Yes, so now you see here a computer that runs the whole system. I will put these windows down to show you what everything is running here. First, this is the QPS control. This is very simple LabVIEW software just to run everything. To run the Josephson, we can operate supracon Josephsons. We can operate NPL bias source that is in Norway, or we can take input from manually set Josephson. It's how Bruno used it in INRIM. Right now we are connected to the supracon Josephson. So for example, we can ask this Josephson for measurement of temperature, room temperature, and so on. Next, we can connect to the sampling software. As a sampling software, we use TWM. And the sampling software is here. Sorry, too many windows. So this is TWM, sampling software developed in TracePQM. And this software, it can control digitizers and also the multiplexer. So here you can select the QuantumPower multiplexer and so on and so on. You can also take a look at the last record of the measurement or to take a look at the results in this window. So next we can also set up the trigger, because we have to trigger the multiplexer, and also we want to trigger the digitizer to start at the same time as the multiplexer. Right now, there is an EDEC generator used as a trigger. And here we can set up our actual scenario, what we want to do. There is several of these. Right now we are, I have set up a scenario when we got one digitizer and we are measuring voltage and current. So it's time multiplexing system. Here you can set up many things, but for example, you can take a look how the waveform will look after the digitizer finish, or you can take a look how to connect everything. Yeah, just basic setup and so on. And you just press, sorry, this window, yeah. And when everything is set up according to your needs, you just press measure. Now it sends commands to Josephson. It's setting the supracon Josephson. Now it sent commands to sampling software and to the trigger. And of course, there happened to be some error, which was not there 1 hour before when I tried to test it. Everything was working, but now it's not working. Yeah, as usual. I don't know, it happens every time. How is it possible? Yeah, something broken down. So I will try to set up it again. Just give me, yeah, I know what I did incorrectly. Just to check here now, I check that the multiplexer is connected. I enable the multiplexer mode. Yes, this is set up. Just to be sure, here I add these two are important. Here are correction files for a divider and for a shunt, because these correction files, they contain the shunt resistance and divider values, but also frequency dependent corrections of amplitude, phase, and everything. This is a system developed in TracePQM project already some years ago. So I hope I have fixed this error. So let's make it again. Not really working as usually. It was working 1 hour ago. Someone has spoiled something as usually. Yeah, now it looks more useful. Yes, now it's going correctly. There are still some errors, of course, because I cannot do everything properly. And now we can take a look at the record, what was sampled by the one digitizer we used. And you see at the beginning, there was sampling of the Josephson waveform. Next, there was sampling of the voltage and current signal. Yeah, after transducing, after the voltage divider and voltage at the shunt in the second and third section. And it was repeated 3 times, so we got 3 results. And here you got averages and okay, now I haven't got 340 volts and 6 amperes, but I was measuring very quickly, so the results are extremely inaccurate. I would have to make 100 or more periods to get a proper value, because this is not coherent measurement. It's just for the show. So yeah, in effect, this is everything. this software is very simple, and most of the development was in the data processing algorithm that splits the waveform into many sections and does all the magic with the data. And I believe that's all. Are there still some questions? Maybe. Yeah, it seems to me that there are no questions, so we are finished. And now we can go to the laboratories, so you can see the system in the real, maybe working, hopefully.